This is Module 5 and it's May 2011 and we're going to be looking at question 14f. This question is looking at the oxidation of iron 2 plus ions to iron 3 plus ions by the oxidizing agent potassium permanganate and the oxidation of ethane dioate ions to carbon dioxide using, again, potassium permanganate as the oxidizing agent. And the first part of the question is just a simple identification test question, but they've made it quite wordy, so it's a bit complicated, but it's just simply your identification test. It says, describe with observations how you would confirm the presence of aqueous iron 3 ions. They could stop there, but they go on just to say how we got those iron 3 ions, which was by the oxidation of the iron 2 plus ions. Okay, so you want to think about what is a test for the iron 3 plus ions. Probably the most obvious one, the most unique one, is the use of potassium thiocyanate or any thiocyanate. The important thing is that there's thiocyanate ions there. So you could say add potassium thiocyanate solution. And then it says with observation, so you have to say what you would actually observe, and that's how you would confirm there was iron 3 plus there. Once you add potassium thiocyanate solution, you would observe a blood red solution. And that's what you get your 3 marks for. You get your 3 marks, first mark for saying thiocyanate ions, second mark for saying blood red, third mark for saying solution. The other option here is that you could confirm the presence of iron 3 plus by the addition of your sodium hydroxide or ammonia solution to get your precipitate. So if you were to choose to add aqueous sodium hydroxide or aqueous ammonia, then you would see a brown precipitate. So you're just recalling your identification test for your iron 3 plus ions. Next part of the question is a bit of a complicated calculation. The question asks us to calculate the concentration of an iron ethane dioate solution by titration with potassium manganate solution. What we can see from our 2 equations is that potassium manganate actually oxidizes both of the ions in that salt. In the salt of iron 2 ethane dioate, you're going to have your iron 2 plus ion and you're going to have your ethane dioate ion. Now, even though iron's positive and ethane dioate is negative, our first 2 equations tell us that potassium manganate actually oxidizes both of them. So first of all, I need to think about what is the formula of my salt. So if you use the charges on your ions and just do your normal swap and drop, you've got iron 2 plus, obviously has a valency of 2, and you have your ethane dioate, which also has a valency of 2. Those are going to cancel down to 1 to 1, and then we swap and drop and you get FeC2O4. So we can tell from this that in every mole of iron ethane dioate I have 1 mole of iron ions and 1 mole of ethane dioate ions. The problem with this is that we have 2 equations to work from here. We don't have an equation for the reaction of ethane dioate with potassium permanganate. We have it separated out, the reaction of permanganate with our iron ions and then with our ethane dioate ions. But as with any titration calculation, the only information that I have is my titer, and that's where I need to start my calculation. If I want to be able to calculate the number of moles, I need the concentration and the volume of something. And I have the concentration and the volume of potassium permanganate solution. So what I can do first of all is work out the number of moles of manganate ions that I have. So I'm working out the number of moles of manganate, and I'm doing N equals CV. Concentration, I'm told, is 0.025, and the volume is 32.2 centimetres cubed, which is 0.0322 decimeters cubed. That gives me a number of moles of 8.05 times 10 to the minus 4. So from this number of moles of manganate, we need to be able to work out the number of moles of iron ethane diowate. Now you can do the next step in a number of ways, but I think it's easiest to see by trying to sort of combine your equations. So I've worked out that it requires 8.05 times 10 to the minus 4 moles of manganate ions to oxidise my iron ethane diowate solution. But what does that value of moles come from? Well, actually it's the total number of moles of manganate ions that's required to oxidise not only my iron 2+, but my ethane diowate ions. And you don't need to always go back to the fact that in your salt, the ratio of your iron ions and your ethane diowate ions is 1:1. So you can see that in these equations, you've got 5 moles of iron 2+ ions and 5 moles of ethane diowate ions. And if we were to combine that, because we have 5 moles of each and because they're in a 1:1 ratio, we're going to get 5 moles of ethane diowate, 5 moles of FeC2O4. But how many moles of manganate have we used in total? Well, we needed 1 mole to oxidise the iron, but then we needed 2 moles of manganate to oxidise the 5 moles of ethane diowate. So in order to produce 5 moles of iron ethane diowate, I needed a total of 3 moles of manganate. Now it doesn't really matter what the rest of the equation is, because those are the only 2 things that I'm interested in. So it's firstly saying that because I have 5 moles of each of my iron 2+ ions and ethane diowate ions, and because they're in the ratio 1:1 in your salt, that you're producing 5 moles of your iron ethane diowate solution. And then it's looking to see how many total moles of manganate ions that you needed to oxidise that. Okay, so I worked out in the previous part of the question that I needed 8.05 times 10 to the minus 4 moles of my manganate. And from this I can work out how many moles of iron ethane diowate solution I have. By just bringing that over, you can see that the ratio is 3:5. So I'm dividing by 3 and timesing by 5 and finding out that I have 1.34 times 10 to the minus 3 moles of iron ethane diowate in my solution. Go back to the question and find out that in order to make up this solution, or how much the volume of solution I had was 25 centimetres cubed. So at this stage you can do one of 2 things. You can say, well, I have 1.34 times 10 to the minus 3 moles in 25 centimetres cubed. So how many would I have in 1 decimetre cubed? To go from 25 centimetres cubed to 1 decimetre cubed, you have to times by 40. So I would need to times my number of moles by 40, which would be 0.0537 moles in 1 decimetre cubed. So your concentration would be 0.0537 moles per decimetre cubed. Or, if I do this working out over here, you can use your equation. Concentration is N over volume. My number of moles is 1.34 times 10 to the minus 3. And my volume is 0.025 decimeters cubed. That's just 25 centimetres cubed and decimeters cubed. And that answer, again, then would be 0.0537 moles per decimeter cubed.